And so next we will introduce how to analyze this single-cell RNA-seq data. So let's first take a look at this sequencing result. And we know from the previous class is that the sequencing result is stored in the FASTQ files. And for SMART-seq data, if we perform the pair-end sequencing, often the read1 and read2 are both from the transcript, as you can see in the figure. So just one from the 5' end, another from 3' end. So, but for the drop-seq data, usually the read1 contains the cell barcode information, and also the UMI information, and also some poly-Ts. And so the position of this barcode for the and UMI for the same technology is usually fixed. And also for read2 is the real transcript sequence, for which you can map it into the genome and knows which gene it belongs to, and then you can combine it with the cell barcode and also UMI to know which cell it comes from. And a special feature for this single-cell RNA-seq is that we need to perform quality control on cells. So you can imagine in the drop-seq experiment, it is not always that one cells are connected with one beads. So if you are pushing the cells in a very slow way, so you might have some empty droplets, which only have the beads, no cells. If you're pushing the cells in a very fast way, you might push one or two cells, multiple cells into one droplet. So you might get some cells with the same barcode. So in the development of the drop-seq experiment, so people mix the mouse cells with the human cells together to determine the multiple rates, as you can see in the figure. So if a cell with both rates for mapping to the mouse genome and mapping to the human genome, which is the purple dot in the figure, it means that this is a multiple cells. This is a droplet with multiple cells. And you can see that if you increase, it is also related to the cell concentration, which if you increase the concentration, the multiple rates will increase. But in the reality, we usually not mix two species. So instead, we just use the transcript number in the cells to evaluate the quality. So imagine if on average, each cell contains 2,000 transcripts. If you see some cells with only a few transcripts, like 10 transcripts, you might know that these cells might be an empty cell. And if you see some cells with extremely high number of transcripts, with like 10,000 of transcript, 10,000 transcripts, you might know this is multiple cells. So, which means that you need to filter out the outliers. And also you can perform some filtering based on other features like the mitochondrial rates, which is usually a sign that the cell is dead. You cannot capture the cytoplasm RNAs, you can only capture the mitochondrial RNAs. And also you can filter cells based on the intergenic exonic rate and also 5' or 3' bias, which means that you can, first when you analyze these data, you need to filter those low quality cells out. Then we'll only focus on those cells with good quality for the downstream analysis. And finally, you can generate it after you cleaning the cells, you can generate the expression matrix like this with the rows as the genes and the columns as the cells. So for the SMART-based methods, you can either use RPKM or TPM to, and also use the risk count for this matrix. And for the droplet-based methods, you need to use the unique UMI count as the expression level. And you could possibly do some normalization first, like for these UMIs, usually people will do some corrections because there might be some existing sequencing errors on these UMIs. And also there are for some single cell experiment, because you are sequencing so many cells, these cells might be in different cell cycles. And so the gene expression can be very varied between different cell cycles. So some people hold the opinion that the cell cycles is a systematic bias, which need to be normalized first. But I think it is actually in some case, the cell cycles will also meaning some biological meanings, biological functions. So which means that it depends the question you are investigate to normalize to decide whether you want to normalize these cell cycle effect. So the first analysis we need to is to realize these cells based on their gene expression level. And usually this need to perform some dimension reduction. And so in the previous classes, you might know that the principal component analysis is a dimension reduction method, which is a linear transformation. And in these classes, we will talk about a new dimension reduction methods named T-distributed stochastic neighbor embedding, T-SNE. So this is the nonlinear transformation of these points. As you can see in these figures, it will give you a better realization of these cells. You can see that cells are similar to each other, are more closely on this plot, on this T-SNE plot, and the cells are different with each other, are more separate on this T-SNE plot compared to the PCA result. So how can the T-SNE achieve a better realization? So let's first talk about the stochastic neighbor embedding, the SNE part. So actually, it is a method to evaluate the similarity of points based on the probabilities. So for a specific point, like the black point in the plot, we can calculate the distance of other points or all other points and to this black point, and we can rank this distance to form a distribution, like the bottom figure. And so the close point to the in the middle, and the far away point are to the tails of this distribution. So then we use this length, this point, to these distribution curves as these similarities. And so actually, you can think in this way: if we normalize these similarities, made them add up into one, actually it is a probability, which means that the probability is how a point will be the neighbor of this black point. So if the probability is higher, which means that it will have a higher chance to be the neighborhood of this black point. And so it will be more in the middle in these distribution curves. So we knowing that these similarities can be represented by these probabilities. So then we talk about how T-SNE is calculated. Actually, in the higher dimensional space, we can calculate the distance of all the other points to a specific point. Here, we named it PJI. I is the point. So this distance or these probabilities can be modeled by a Gaussian distribution for here, the black curve. And so what we're trying to do is to project these points from the higher dimension to a lower dimension. So in the lower dimension, you can use some other distributions to calculate these probabilities. So for here, because the terms T-SNE, we use student T distribution to calculate the distance in the lower dimension. And as you can see in the figure, it is the red curve in the figure. It has a long tail. So by doing this, so you can see that if a point is in the middle of these distributions, which means these points are close to these to the points you interest. So in the T distribution, it will be more even closer. And if a point is far away, like in the tails of the Gaussian distributions, so in the lower dimension, in the T distributions, it will be even further because it has a longer tails. So by this transfer, you can see that the closer points are more closer, and the far away points are more far away for these distance evaluations. And finally, we want to make these distributions as similar as to each other. So in the statistics, we can calculate the Kullback liberal divergence between these two distributions. And you can do some iterations to minimize this divergence and for all the points. And finally, you will get the T-SNE plot. So a few points we need to emphasize for the T-SNE is that actually the final similarity in the low dimensional space is based on the T distribution. So that's the name it's come from. And we need to scale the similarity, scale them into one to a probability. So by doing this, after the scaling, the similarity of x to y will not be equal to the similarity of y to x because they are using different scaling methods. So usually, if we want to calculate the distance, we just average the two. And also this method, you can imagine it is similar to MDS, but MDS use a linear evaluation, you use the Euclidean distance, but the T-SNE use a probability distribution, which is a nonlinear. And last, is that the T-SNE calculation is very time consuming. So people usually do not calculate the T-SNE directly on the genes because it takes very long time. They usually first perform the PCAs to do some dimension reduction first to select the top significant principal components, then perform the T-SNE on these components to speed up.